This is going to be chapter 14, Intro to Acids and Bases. It'll be using your notes packet for that, at least the front page of it. Some calculations of pH and those things. So you probably don't know a ton about this stuff. It'd be fairly new stuff, I would think, in general. So here's the first part of this. Giving you some reactions here, saying identify the acid, the base, conjugate acid, conjugate base in the following reactions. So these are chemical reactions of an acid and a base. So it's an acid-base reaction each time. Which always makes, not always, usually makes conjugate acid, conjugate base. So our definition of acids, if I go down here, definitions of acids, there's three different ones. I basically just say, and it's really these two, acids are hydrogen ion donors or givers. Acids are hydrogen ion donors. Okay, they're giving away H plus ions. Bases are hydrogen acceptors. So acids are giving a hydrogen, bases are accepting. I will tell you that when you have H plus ions in water, and all these reactions happen in water, things are not acids and bases unless they are in water. They have to be aqueous to be acids or bases. H plus ions in water make hydronium ions. These are the same things. H plus ions, hydronium ions are the exact same things. Okay, so you're going to see both those things. Think of them as the same things. So H plus ions, when they're in water, make hydronium ions. All right, so we look at these. We're trying to figure out which thing gained a hydrogen, which thing gave away a hydrogen. Well, if you look at NH2 negative, it became NH3 over here. This lost a hydrogen, so hydrogen's being transferred that direction. So this is our acid. This is our base. The conjugate acid, okay, is this base is gaining a hydrogen. This is now the conjugate acid of this base. It has the ability to give away a hydrogen. It's got an extra hydrogen now. This thing does not want to give away hydrogen. It's got a negative charge. It really wants to gain a hydrogen. So it is the conjugate base of this acid. So once the acid loses the hydrogen, if it's a weak acid, strong ones don't do that. If it's a weak acid, its conjugate base is formed once it loses its hydrogen. Down here, this is HF, which is one of the weak acids. So we know it's an acid. Notice you're getting H3O plus, so the hydrogen is going from there to there. Water's a little weird. It can gain or lose a hydrogen. Okay, so there's a hydrogen being transferred there. So this is our acid. This is our base. This is the conjugate acid. It's got an extra hydrogen to give away. This is the conjugate base. It's got a negative charge, which means it can gain a hydrogen. It can act as a base. The F negative can act as a base a little bit. Down here, HNO3 and AOH. There should not be a negative charge with that. Sorry, that negative should not be on there. If you look at this, this is actually a strong acid, strong base reaction. So the H and the OH are going together. So really, this is giving to that. This is our acid. This is our base. There is no conjugate acid and conjugate base in a strong acid, strong base reaction. You'll figure that out later why that is. But whenever we have a strong acid, strong base, there's no conjugate acid or conjugate base in that reaction, which you'll discover later. All right. Acid-base dissociation or ionization. First thing, you probably need to know your strong acids and bases, which are down here. Okay, they're listed down at the bottom of your sheet. So the strong acids, HCl, HBr, HI, notice HF is not on that strong acid list. And then HNO3, HClO4, H2SO4. The other one that a lot of times on there is HClO3, is also considered strong acid. So there's really 7 strong acids. Those 100% dissociate. These strong acids 100% dissociate. Okay, the strong bases are basically OH negatives with family 1. So lithium, sodium, potassium, cesium, and the bottom 3 of family 2, calcium, strontium, and barium. Those are the strong bases. They have OH in them with a family 1 or bottom part of family 2 metals. Those are your strong bases, and some of these actually are considered kind of marginally strong. So acid-base dissociation, couple ways we can show this. Okay, there's 2 ways we can show this. So number 1 would be if we have let's say we have a strong acid like HCl. which would be aqueous. Has to be an acid. If we put it in water, or if it's in water, I guess we made it aqueous. In water, it makes H plus ions, which are aqueous, instead of negative ions. It's a one-sided arrow. There's 100%, or at least close to it, 100% dissociation of those HCl's. 100% dissociation of those. That's why it's strong. You get lots and lots of H plus ions, meaning it's a stronger acid. The other way we could write that would be HCl plus H2O makes hydronium ions, which remember are the same thing as H plus ions, plus Cl negative. All right. The AP test will almost always show you the acid plus water. So in this case, the water is acting as a base. It's taking a hydrogen from there. This is your acid, this is your base, going from there. If it was a weak acid, so you might want to put all these examples on here. If it was a weak acid, for example, like HF is a weak acid, you would see a two-sided arrow forming H plus ions plus F negative. This is not 100% dissociation. It might only be like 3% dissociation. Only like 3% of these molecules dissociate into those. 97% stay together as a molecule. They don't dissociate. So a weak acid, they don't dissociate. Strong acid, they do. The other way you could write this, again, would be HF plus H2O, two-sided arrow, makes hydronium ions, same thing as H plus ions, plus F negatives. If this is a weak acid, that is its conjugate base. Weak acids and bases have conjugate acids and bases. Strong ones do not. We'll get into that a little bit later down the road. Bases, if you have like NaOH, dissociates. Oh, it's 100% dissociation because it's strong. So you put it in water, it's 100% dissociation. So you get lots and lots of OH negative ions, meaning it's a strong base. The weak bases, if you remember from the beginning of the year, the weak bases will be some derivative of ammonia, NH3. Okay, so NH3, we have to put plus water. Okay, plus water. Let me write this as HOH. Again, that's a weak base. This has the ability to take a hydrogen from water and make NH4 plus OH negative. Put a big star next to this. This is really important for you to know this dissociation. Weak base, this can take that. Again, it's making OH negative ions, so it is a base. Most things you put in water don't take a hydrogen from it. This does. So if you see anything with that NH in it, it might be like CH3, CH2, NH. If you see that NH on there, it has the ability to take a hydrogen from water and make OH negatives. Again, if this is a weak base right here, this is the conjugate acid. This thing has the ability to give a hydrogen away and act as an acid. So we'll show dissociation for about everything we do, so get used to doing that quite a bit. Next thing, amphoteric or amphoprotic. If we think about an H plus ion, an H plus ion is basically just a proton. There's no electron, there's no neutron on an H plus ion most of the times. So acids are actually proton givers, proton donors. Amphoteric means substances can act as either acids or bases. I'll tell you, water is a great example of that. Water has the ability to give a hydrogen, take a hydrogen, and make H plus ions or OH negative ions. So you'll see some of those as we go along. This is the auto-ionization of water. I don't really like the way I have that written. So auto-ionization of water means put some water molecules. Water does dissociate a little bit, but not very much. Kind of lagging a little bit. Every time I look back at the screen, it's a little slow. Water does not dissociate very much. It does not split apart very much, but it does a little bit. So in water, the concentration of H plus ions, the molarity of H plus ions is 1 times 10 to the negative 7th molar. And this is also 1 times 10 to the negative 7th molar. That's a really, really small molarity. Water itself is 55 molars, 55 moles of water in a liter of water. So that's a small amount that dissociates. Like the percentage is like 0.000000002% of water molecules dissociate. So there's not many hydrogen ions in water, not many hydroxide ions, but they are equal. Okay, they are equal in that case. So, but water does produce some of those. Okay, water does produce some. Remember, water is a liquid. These are both aqueous. So if we write our K expression, Kw, the K of water, is concentration of H plus to the first power times concentration of H negative to the first power over nothing because water is a liquid. Well, if we plug in that and that, we get 1 times 10 to the negative 14th. That is called the Kw of water. That is true at 25 degrees Celsius, not true at other temperatures, but that is the Kw of water. I should talk about a little bit about our K expression. Let's say we had that HF before, where I shown HF in water making hydronium ions or H plus ions. So if we were writing our K expression for this, it'd be called Ka because this is an acid. Concentration of H plus ions or hydronium ions. Concentration of negative ions over concentration of our weak acid. Okay, so we're going to be writing that a lot as we go through here. For water was a liquid, so we don't do that. This was aqueous, making hydrogen ions in that. So the bigger this K value as you go along, you'll realize you get more H pluses, more F negatives. If the K value is bigger, it's a stronger acid. All right. We'll talk a little bit about pH in the next video. Have a good day.